So since it's a conditional, we know that, and it's also a conditional that we don't find in the premises. We know that we'll have to introduce that conditional into our derivation. So conditional introduction is the assumption rule we'll be using to start things off. And knowing the schema for conditional introduction, the assumption is going to have to be this part. And then what we get to is this part. So our assumption's JA. So now we can consider this lined area a subderivation of the overall derivation. And if we complete the subderivation, we've basically completed the whole derivation. And now it's a derivation with two premises instead of one, effectively, right? With this assumption, we've added a second line that we can just consider to be true. Fortunately, this also lets us use some elimination rules to simplify that first premise. So we can use our conditional elimination. To get this amazing that amazing line there. And then we have to use conditional elimination again and again. So at this point, you might be asking, what are we working for here? Are we just eliminating these conditionals because we can, or do we have a purpose? So the answer is we do have a purpose. And so one thing you guys are going to become sort of attuned to, or you should pay attention to, is now that we have our negation introduction rule that looks like this. Anytime you can find a contradiction in derivation means that you can solve that derivation. It's that powerful of a rule. So there actually is a contradiction in this first premises. So that JA not JA. So if we can unpack that and get JA separate and not JA separate, we found a way to use, well, we'll be able to use that negation introduction rule to introduce whatever we want into our derivation. Okay. So strategizing takes a little bit of a different turn with negation introduction. So several conditional eliminations in a row, and we have our not JA by itself. Particularly bad at drawing things today. I'm really sorry. I mean writing. Oh yeah. Okay. Now that we have that, all right. I actually should have waited to, no, that's all right. This is cool. Okay. So I'll show you guys how to do a assumption within assumption, and also use negation introduction to pull off a trick. Because as you'll notice, this is not a negation. That HA is just a unnegated HA. We can still use negation introduction to derive unnegated things, though. That's how magical this rule is. So if we want to derive HA using negation introduction, let's prove that negation HA leads to a contradiction.
Why are we negating HA?
In the assumption,
Yeah.
I'll show you. So that will get us double negated HA, right?
Wait, how will it get us double negated HA?
With the negation introduction.
Oh,
So
so Q can be like any well-formed formula, and then as long as there's a negated well-formed formula above it, it'll be a double negated.
yes.
Oh,
So
cool. Okay.
yeah, and if we double negated HA, it would be triple negated when we introduced our negation. Okay. All right. And then we can use negation elimination to get the unnegated version of that. Then we finish off our derivation. 2, 2, 9. All right. So this part here, where the yellow line is a really common way to derive an unnegated thing from a negation introduction. So there'll be a lot of times where to solve a derivation, you need to arrive at an unnegated line using negation introduction. So what you can do is start with the assumption. Start with the assumption with the negation attached, and you prove that that leads to contradiction, which lets you add another negation to that negated thing. And then you could remove both of those and get the overall unnegated version.
Is that a double negated HA? Is that in the assumption? Not the conditional introduction assumption, but that's not in the negation introduction assumption, right?
Yeah, the negation introduction, that's just a single negated HA.
Okay, so but the double negated one's outside of that.
Yeah. Oh, it's outside of that line. Yeah. That scope line only goes to the JA. Oh, it's only for line 6 and 7.
Okay.
Yeah. And Vivian's got a question. Okay. Why can't I? I'm still confused about why we negated HA. So, let me write down the schema for negation introduction. So it allows you to assume Q, and once you get a contradiction, or assume P, whatever order you want to do the expression of variables, allows you to add a negation to that. So in this problem, our Q was negation HA because we wanted to add another negation to that negation HA so that we can get a double negated HA which is then the equivalent of HA by itself. Because negation introduction doesn't let us, right. So if we assumed a non-negated HA, then what we would get is negated HA, right? But we don't want that.
Oh, JA and negated JA, that's P and negation P, and then Q is negation HA.
Yeah.
Okay.
Okay, does that make sense now, Vivian?
This sounds to me like a stupid question, but why couldn't we just assume HA and then close off that subderivation and then just add a conditional introduction to get JA, then HA? Like, why do we have to do the negation introduction?
So, because HA doesn't exist anywhere in the premises or the assumption. So it's nowhere near the top of this. So we need some way of introducing HA into the derivation. And the only way to do that with our rules of inference is negation introduction. So negation introduction is the only rule that allows you to introduce new things to a derivation, like totally new well-formed formulas.
So you couldn't just assume one thing and then close it off and then introduce it into your derivation.
You mean, so using conditional introduction?
Well, no, like you couldn't just assume for line 6, for example, like the same sub derivation and then just assume HA and then close that off. And then the next line be like conditional introduction.
No. So even though, yeah, I sort of what see what you're saying, because we can assume anything, right, and prove that contradiction because the contradiction already exists before that subderivation, basically. But the only thing that we could assume that would get us what we want is negation HA, because what we want is this unnegated HA, and to get that, we have to assume the opposite of negation introduction. So negation introduction as a rule of inference is sort of informally saying this. It's saying, look, if we assume something, we get a contradiction. So the opposite of that thing has to be true. Does that make sense, Madison?
Yes.
Okay, cool.
So as long as you have what do you call it when it's like the JA and negated JA? What's that concept called? Like
Oh, that's a contradiction.
okay, contradiction. So as long as you have a contradiction somewhere in the equation, you could pull in any atomic that you really want to.
Yeah. So as a strategy, that's something you can think of doing. So I'll just write that here. This is a contradiction.
So is this like the only rule that and disjunction introduction that we could pull in something random?
Yes,
Okay.
that's right. Disjunction introduction is another one that you can do that. But disjunction introduction, it's even harder to get what you want out of it because we can't get like atomics, basically. Like we can't bring a new atomic into our derivation.
Okay.
Okay, cool. So the rest, so what we'll do now is, I know some of you emailed me with homework questions that you were having trouble with. So let's do that now. We can take up any homework questions that you guys had trouble with, as long as it's not the graded ones. Sorry, my headset just like. Did anybody say they had a question? Judson, I think you mentioned you had one.
Yeah. So I had one. I don't have a specific problem, but I just have issues with pulling in things that are not originally in the premises. So
Right.
like,
So the
if the
assumption rules.
if the conclusion has atomics that are not in the premises, I just have a little issues with that. So I was hoping maybe you could do like an example or something, because unfortunately, the one that one of the ones that I'm talking about is the ones that are graded. So I was hoping that you could do like an example.
Okay. So one where atomics don't exist in the premises. So which one is graded for again? Because I can't log into Blackboard.
So number 4 of
Okay.
8.1, you include you have to, in the conclusion, it has an extra well-formed formula that is not in the premise.
Yeah. Yeah, I see that. Uh-huh. Okay, let me come up with one similar to that. That won't give away the answer to that. Okay. Hmm. Okay, yeah, here's a good example. Okay, so this one is sort of similar to what the type Judson's talking about here. We've got uh, a premise that's a lot smaller than this huge conclusion, but we've only got one premise, and a lot of those atomics aren't in the premise, right? Meaning we have to introduce them somehow into our derivation. So whenever you see that, you're going to be thinking about assumption rules, uh, or you know, uh, disjunction introduction. Okay, I like thinking about assumption rules because they're really straightforward when you think backwards. All right. Well, the main connective here is, arrow. So arrow introduction. We know the schema for arrow introduction is something like this, or exactly like this. That helps us figure out what to write down. So we've got the P part here, and that would be this whole well-formed formula, right? We know we have to assume that in order to get the conditional that we want. And then the Q part is this guy here. So we have to get that in order to derive what we want. All right, that lets us write down our little subderivation there that I didn't give enough room to write the numbers next to. So okay. So this is the P part of our assumption rule.
Wait, so you have to assume the whole antecedent?
Yeah.
Oh, okay.
Yeah. But that's what you want to do also, because it gives you more things to work with, right? So the more you can assume, the better. And then GB is the Q part. So we don't know how we're going to get that yet, but I have some ideas. All right. So now we can consider lines 1 and 2 basically given to us. And from here, it's sort of a much easier derivation to figure out, the subderivation. So right away, we've got this conjunction we can get rid of and just get FA by itself. And then from there, we can get GB. And from there, we can use disjunct introduction. On line 4. Wait, I can't count. And that would be 25 for the introduction. Really actually straightforward derivation despite maybe looking scary at first, right? Because we have this huge conclusion with a lot of, there's 3 atomics in it that don't appear anywhere in the premises. So how are we going to get it? Here it's pretty straightforward. 2 of them just appear in the assumption, and then one of them is introduced through disjunct introduction. Did that help you, Judson, with what you're asking about?
Yeah, that helps. But on number 4, it has the you have to do conditional introduction twice, it looks like. So that's kind of, I'm confused how you pull it in. My question is more about how you pull in an atomic that's not in a premise with a conditional introduction.
Well, the same way we did here. So if I can't say much more without giving it away. Yeah, but
That's fine. That's fine.
yeah. Something that will help you is just to think that not every assumption you have to use it, right? You can just make an assumption and not use it anywhere else in the derivation, just have it be introduced or part of your conditional that you're introducing. Yeah. So like in this derivation, for instance, 2 of the atomics, like this whole part here doesn't come into the derivation at all. It's just like part of the assumption so that we can make the conditional that we want using this rule. Vivian, did you have a question? I think Vivian had a question. No, okay. All right. Any other homework related questions or things from your homework so far that you guys have had trouble with? Because if not, I can just go over some of these homeworks with you guys. The non graded ones, and we could take them up together. I'll just choose them at random, but it'll be better if you guys have like an idea of ones that you struggled with or that you tried and want to see done over Zoom.
I have a question about the one that we just did.
Yeah.
So how much can we assume? So we assumed that whole FA and DC and EA.
Hmm.
So theoretically, could we just like assume the whole thing?
There's no
Like
limits. Yeah.
so how is there like, I guess I'm just like confused about what to know, like what to assume, and
Yeah.
then why
So,
did you assume that first?
so, right. This is going to be the trickiest part for you guys to think around. It's like the one part of doing assumption rules that everyone has difficulty with. But you want to think of the assumptions as not something you think about very hard. Because what you assume is determined by what you're trying to get. And for this derivation, since you have to assume the antecedent to the conditional, we just have to assume the whole antecedent here. So if the antecedent was like a huge well-formed formula with 10 atomic assertions, then we would have to assume that. So it's not really what should I assume? It's really what do I have to assume here to get the conditional that I need?
Okay.
Does that help, Vivian?
Yeah. What is there? Would there be another way to do it? Like, could you? My first thought would be to assume FA and GB like as lines 2 and 3.
Okay. Uh,
But I guess it's just something I'm gonna have to get used to, like to assume that much
yeah,
in the beginning.
right. So it's just for assumption rules, you have to think backwards with them. So it's not
Okay.
really that. I mean, it's crazy to me to think of anyone not doing that. Basically, I think it's possible, but uh, at least thinking strategically as far as what you need to assume, you have to look at what you're trying to get first, and then making up your assumption from that.
Okay.
Uh,
Okay.
yeah. So looking,
That makes a lot more sense.
yeah. I'll show you guys like a really simple example here. And this is one that I think the textbook uses. Uh, so if you guys remembered, or maybe we didn't cover this, but logical truths, we can have, it's possible to have arguments with no premises, right? Valid arguments with no premises. So if you remember, that sort of well-formed formula is called idempotent. And if you think of it semantically, it's always going to be true, right? Because no matter what truth value you assign the those atomics, that main connective is always going to be true. So if FA is false, you have two falses, and the arrow symbol comes out true under that case. And if it's true, if FA is true, then you have two truths, and it's also true. Well, think about validity. If you have a conclusion that's in all possible models true, then there's no way for that argument to be invalid, even if you don't have any premises. I mean, especially if you don't have any premises. If our derivation system is complete, then it ought to allow us to derive these sort of things. Now, obviously, if there's no derivation, I mean, no premises, where do we get these atomics from, right? So the only place we can get them from is using assumptions. So I'll show you how it would work for this. So the question is, what assumption am I going to make? Well, that question means what assumption rule am I going to use? And the assumption rule here is arrow introduction. Okay, if it's arrow introduction, what does the assumption have to be? it has to be the antecedent. So FA. Now, there's a rule that's going to let us reiterate things. Because once we have something already in our derivation, we can just say it again, basically. So let's use that rule right now. Okay. We've taken no premises and just came up with an atomic using our assumption rule, and then sort of from all appearances came up from nowhere this FA conditional FA. So an example of like how you would invent atomics or bring atomics into derivation where really there weren't any to begin with. And there's a lot of these. So some of the more difficult derivations are all, these are called theorems. So proving a theorem, starting from no premises and just a conclusion, and showing that you can use the two assumption rules to prove that, prove that theorem.
So anytime you want to bring back up an atomic, you can just use you can put the R on this, like inside the line.
Yeah, I was going to teach you guys that rule next week, but you can use it now. You don't need to. None of the questions will ask you to do it. But yeah, so you can use the R rule for reiterating. Just saying again what you've already proven. One thing to keep in mind, though, is the scope limits. So you can't reiterate something that's outside of the scope of the line you're talking about. So for instance, if I had a line 4 here, I couldn't reiterate FA. Right? Not allowed. Because that's outside.
What if you had a subderivation off of what if you had an assumption and then an assumption beside that, like two side by side? How would that work?
Two assumptions. You mean nested, sort of like how we have them in this derivation?
Yeah.
Okay. We can do another example of those because, oh, right, you're asking for question 4. Yeah. Let me think of another one that would use that. Okay.
Well, like I'm just wondering if you have a subdiv, or like I don't know the right words, but if you have a line, you know how you have the line that shows that you're using the assumption rule,
Yeah.
and then you make another assumption beside that. Can you cite a line that was in the assumption to the left, or does it
Yes.
have to?
Yeah.
That's all I need to
So
know. You don't have to give
yeah,
me.
yeah.
I just
Yes,
didn't
you
know if
can.
that was like legal or not, so that's why I was
Yeah.
confused.
So the further to okay, let me give you guys a general. Maybe this will be helpful actually. So we've got a bunch of assumption lines. Okay. A1, A2, A3, A4. Going from left to right. Maybe this will be helpful to screenshot. So going this way, permissible. But going this way, So, for instance, in the scope line of A1, you can't cite A4. Is not access A1. But A1 is accessible from A4. So as you close off assumptions by using the two assumption rules, you get rid of the assumption from the derivation and anything derived by it. So anything derived on line A4 for the fourth assumption is not accessible after it's been closed off. Does that help you guys a little bit?
So I have another question about assuming things.
Mm-hmm.
What's like another strategy to bring in an atomic well-formed formula if you don't have a contradiction and it's not in the premises? Other than like just assuming it, or I guess a disjunct introduction, but
Yeah, so assuming it as part of... Here, I can show you guys an example. Okay. Here we have... Yeah, this will be good. Okay. Premise one. So we've got one premise here and a conclusion. So let's think backwards here. The main connective is conditional. That doesn't exist anywhere in the premises. We'll have to use conditional introduction. So we've got the antecedent, P, and the consequent, Q. All right. You'll notice that in this conditional, the antecedent isn't anywhere in the premises, right? So we're going to work our magic here, but it's not really magic because it's just what we have to do. Okay. So we have to assume MN. And we have to get to GB biconditional CD. Okay, any idea how we can get there? Well, we're not going to use line 2 at all because this biconditional is in line 1. All right. Did that help you, Maddie? Or did that help illustrate what you were asking about?
yeah, so you can assume the antecedent even if it's not in the premises as long as it's the antecedent.
Definitely, yeah. So
Okay.
whatever the antecedent is, you just have to assume that. Even if it's
Okay.
nothing you want, or even if it's not on the premises, it just comes along with getting that conditional.
Okay, thank you. That clears a lot of stuff up.
Awesome. Does that help you too, Judson? Oh, James just messaged me. I'm still struggling to understand how to do all three of the 8.1 questions. Never mind, I actually figured it out. Okay, cool. How long ago did you send that? It doesn't show me when the timestamp is.
It was a while ago, but it's all good.
Okay, all right. I gotta figure out how to have these windows on top of my screen because as soon as I start writing, they'll disappear. Let me see if I can do that really quickly. No. Okay, whatever. All right. So we just have 5 minutes left. Do you guys have any more questions about like homework struggles or anything you're having trouble with? Okay. Well, let's just quickly go through question 1 on 8.1.
You hear me?
James? Yeah.
Yeah, I have a question. So,
Okay.
is it possible, like in the homework, if they give you like a bunch of stuff in the premises that you just never use? Is that like a thing that happens sometimes?
Uh, Not usually, I would say. It can happen though.
Yeah, because like using assumption rules and stuff, like I feel like I found a way like to where there's like a lot of stuff that was put in the premises that like didn't really come up. But I don't know if that's like just because I did it wrong or what.
Right. Yeah, that's a good point. Is it the non-grade? Is it the non-graded homework you're talking
Yeah,
about?
it's on the graded, but
Yeah.
I don't know.
So yeah, uh, I would say that if you found a way to do it where you don't use all the premises, then that might indicate that you did it wrong because the person who came up with these questions wouldn't like use that to trick you at all. So Michael Dixon, who made this textbook, he taught me for my advanced logic class, and I had to do a lot of assignments. It was a pretty crazy class. It was the hardest class I ever did. It had 16 take-home assignments. Each of them took like 6 to 8 hours to do, and then a take-home midterm, which took me 20 hours to do, and then a 15-page essay at the end of the course. So that's grad courses for you, you know, but I really loved it. But anyways, out of all those problems that I can remember, none of the tricks he put into the questions had to do with filtering out which details were relevant and which details were irrelevant. He only put in relevant details in the questions. And I think that all of these questions, you're probably going to have to use all the premises to complete them. So that was a long-winded answer, but yeah. So James, if you found a way to do the question without using a premise in the argument, then that might indicate that you've done it wrong or that you are a genius and you
Well,
figured a way to.
the problem is that like it gave us three premises with like a lot of different atomics, but then the conclusion's only one atomic, and like it's
Oh, right. Yeah, yeah, yeah. Okay.
so like they give us a bunch of different atomics that like just I don't really see. Like I completed it, but like there wasn't really a reason to bring up all the other atomics.
Yes,
I
and that's going to be the case for that one. Yeah.
okay.
So, yeah, yeah. So you don't have to use all the atomics for sure. But
Okay.
as long as you're citing one of the premises at least once, then
Got it.
yeah, that's a useful thing to bring up too. So if you're trying to figure out whether you guys are on the right track, uh, try make sure that in doing the question, it's going to be useful to pay attention to whether you've cited all the premises. It's not a requirement to do that to finish a derivation. It's just that the way the person who's thinking of these questions isn't going to make you have like 5 premises that you don't use, basically. All right. So if you guys don't have any other questions,
I have one question.
Oh yeah. Okay, Judson.
So if you're doing disjunction elimination, does the R value necessarily have to be different from either P or Q, or can it possibly be the same?
The R value.
Like you do P or so you do P to, or like you do it's P or Q, then you do P to R, Q to R, and then R is what you get at the end. So I'm just wondering if like
Oh,
R
right,
can
right.
R be can R be the same thing as P or Q, or does it have to be something different?
It doesn't have to be something different. Yeah, I know what you're saying. So, here, right. Let me do an example.
Yeah, if you can't tell, most of my questions are just about the rules. Like I don't like sometimes the rules just get confusing to me. I don't know, so that's why most of my
Yeah,
questions
so
are.
anything can fit into those variables. So P can be the same as, so when we used, for this one, when we used arrow introduction, P and Q in the schema were the same thing, right? FA is the same, or P is FA and Q is FA. So there's no restriction on, those things being identical. So, but let me just write out like an example. And this is a way that you are going to find that you eliminate some disjuncts. So that's one way to use disjunct elimination. Did that answer your question, Judson?
Yeah, that does. Thank you.
All right. Any last questions?
Not a question, but my brother's been listening in and he's just as
Wait, what'd you say?
he's just as amazed at like how hard this class is as me.
Oh, awesome.
Yeah, right. He thinks it's
Yeah.
interesting though.
Yeah, now that you guys are all back with your families, you can brag about how hard logic is. Yeah. Okay, cool. I'll see you guys. Good luck with the homework. I'll see you guys on Monday. Bye, guys.